All right, let's start getting into students' T distribution. Like you saw in the video for Wheelam-Silly Gossett and the Guinness Brewery, the T distribution is a distribution used to estimate a population when the sample size is small, typically a sample size of less than 30. It'd be best if I could take a large sample to get a big picture of the population, a more representative sample. But oftentimes that's not the case. Sample is expensive. What if I can only sample a small amount of things, like 4, 5, or 6? Given a small sample size, we have a lot of variability because I haven't looked at a large part of the population. It's still helpful to conduct inference given a small sample size, but we need to use a different distribution. I need to use the T distribution as opposed to the Z distribution in normal distributions. We use T distributions, like I said, when the sample size is small or when the population variance is unknown. I have more error when I don't know the overall population variance. When I'm using the sample variance, the sample standard deviation to estimate the population variance. More error, more variability, T distribution. Now, more information about those small sample sizes. According to the central limit theorem, according to CLT, sampling distributions become normal given a large enough sample size. We're allowed to use the Z distribution if n is greater than 30 because the T distribution and the Z distribution are pretty much the same thing given a large sample size. For smaller sample sizes, an unknown population standard deviation for unknown population variance, the T distribution is used. For more variability, that comes from having a smaller sample or using the sample variance to estimate the population variance, using the sample standard deviation to estimate the overall population standard deviation. We use what's called the T distribution. One more piece of information on the T distribution. T distributions have n-1 degrees of freedom for a sample of size n. There are n-1 independent items in a sample of size n. N-1 of them can vary, but the last one, the nth one, would be locked in. For example, if you have a class where you take 5 tests, and I tell you what the average of those 5 test score was and what 4 of the tests, their actual scores were. If you know the average of 5 tests and 4 of the individual test scores, the 5th one you can find pretty easily because the last one, the 5th one, is locked in. Once you know 4 of them and the overall average, you can find the 5th test score pretty easily. The 5th one is not variable with the other 4 were. They're independent. In a sample of size 5, there are 4 degrees of freedom. 4 of the tests can be independent. 4 of the tests can vary. They can do whatever you want. The 5th one's locked in. So in a sample of size n, there are n-1 degrees of freedom. Every T distribution has what's called a degree of freedom based off of the sample size, and it's n-1 degrees of freedom for a sample of size n. Let's talk a little bit more about the relationship between normal distributions, Z distributions, and the T distribution. On the screen behind me, I have the graph of the normal distribution, the bell curve in blue, with the red T distribution shown along with it. Let me share with my screen with you here, and we can graph the same thing using Desmos. All right, so on the board behind me, let's make sure this matches. I'm going to put the normal curve in blue and the T distribution in red, just so it matches what I have on the board behind me. Now, the normal distribution, we've seen a bell curve like this before. It has 2 tails on the left and the right. It's centered at 0. It's symmetrical. The left and the right halves are the same. The probability distribution, the normal distribution, has a sum of 1. Every distribution has a sum of 1. Now, the T distribution looks somewhat similar, but with a few minor key differences. Do you see on the left and right, on the right here and the left here, and the 2 tails, it's a little bit fatter. The T distribution has what's called fatter tails and a smaller peak. It doesn't quite get up as high as it does for the normal distribution. Now, why would that be? in the t-distribution, we have a greater chance of extreme values, values that are more atypical, values further from what's expected, more extreme values. Those extreme values live in the tails because they're further from the center. They're more atypical. They're further from what we'd expect. We have a greater chance of an extreme value that lives here in the right tail and in the left tail. If you have a greater chance of an extreme value, those two tails have to have a greater probability, and thus fatter tails here in the red t-distribution on the right and left. Because we have a greater probability for an extreme value in the tails, that means I can't quite get up as high in the middle while still also adding up to the same one that every probability distribution has to have a sum of. If more is in the left and the right tails in T versus Z, that means there's less to make the peak with in the middle for in the T distribution when compared to the Z distribution. More probability of extreme values given a smaller sample size. If I had a smaller sample size, we're going to have more variability. I have a greater chance of extreme values. Those extreme values live in the tails, further from the center on the left and the right. If there's a greater chance of what's on either end, there's less of a chance of what's in the middle. I can't quite get up as high because more of the probability is spent on either ends. Every distribution has to have a sum of 1, so if I have more in the tails, I have less in the middle. All right, now let's talk a little bit more about degrees of freedom. Desmos is graphing a t-distribution so long as I tell it what the sample size is, what n is. Based off of n, we can graph that t-distribution like you're seeing in red. As I increase the sample size by moving this slider to the right, you can see that that red curve starts to approximate the blue curve. As sample size increases, the t-distribution becomes more like the normal distribution. By central limit theorem, after about 30, after a sample size of 30, they're roughly the same thing. By central limit theorem, every sampling distribution becomes normal given a sample size of approximately 30. 30 is kind of that convention for us to use. For smaller sample sizes, anything less than 30, there is a significant difference between the t-distribution and z-distribution. You can see the fatter tails here on the left and right, with a smaller peak in the middle. T-distribution versus z-distribution. You can see the red t-distribution and the blue z-distribution. Both are symmetrical with a center of 0. However, the t-distribution has a greater chance of extreme values due to larger variability, due to smaller sample sizes. Thus, we have fatter tails on the left and the right, with less of a peak in the middle. If more lives on either side on the left and the right, there's less to make the peak within the middle. All right, this last set of questions, we're going to use your t-table. If you don't have a t-table, go ahead and grab that, please, that laminated t-table. I will share my screen and show you what we're talking about. Here we can see the t-table. It says table T right here to the left. Down along the rows, we have the degrees of freedom. From 1 degree of freedom, it increases by 1 till 30. Then it starts to go up by more and more as I move down the rows, till eventually I hit 1,000 degrees of freedom down here. Across the columns, I have different tail probabilities. 2 tails would be in this top row. 1 tail would be in the bottom row. I have the confidence levels, which column applies to which confidence intervals, which confidence levels for specific confidence intervals here in this bottom row. The first column is for an 80% confidence level. The second column is for a 90% confidence level, and so on. So for this first question, find each critical value of the t-distribution, otherwise known as t star. What's the critical value of our t-distribution, t star, for a 95% confidence interval with 21 degrees of freedom? So in a distribution, I'm trying to estimate a population parameter, so I take a sample. Let's call that sample statistic x bar. I want there to be a 95% chance that I've captured the overall population mean, mu. So I'm going to add on the margin of error, subtract off the margin of error. I want there to be a 95% chance that I've captured that population mean, or population parameter. Adding on the margin of error and subtracting the margin of error. What's the percent chance that I haven't captured the mean? What's left over for the two tails? So my error, the chance that I haven't captured the population parameter, is the other 5%. Notice I have two tails. If there's 5% total error, and I split that evenly, symmetrically across the two tails, half of our error, alpha divided by 2, 5% divided by 2 is 2.5%. I want to know, what's that t-score? That puts 97.5% of the distribution to the left. So using our t-table, we have in two tails, 5%, two tails, 5%, which is the same as each tail, one tail having 2.5%. Two tails together having 5% is the same as one tail having 2.5%. Those both mean the same thing here in this middle column. Or you can also look up the bottom row. Our confidence level for a confidence interval is 95%, meaning the same thing. We have, 21 degrees of freedom. So my t-score is 2.080, right here in your t-table, pretty much right in the middle. A t-score of 2.080, 97.5% of the distribution to the left. Okay, back in question 2. Question 2. Do another example of this. What's the critical value of our t-distribution? What's our t-star value for a 99% confidence interval with 18 degrees of freedom? Let's draw another distribution. I'm creating a confidence interval to estimate some parameter. I want to know more about the mean of a population, so I take a sample and calculate the sample mean x bar. Sampling is random. There's variability. Maybe my sample mean is more than or less than what it's supposed to. There's a margin of error I'm going to add on. Subtract off. I want to capture 99% of the distribution. So my error, my alpha, is 1%. There's a 1% chance that I haven't done this, that I haven't captured this interval. I haven't captured this population parameter within the interval. Confidence intervals are two-tailed, so let's split that 1% into the left and the right tails. There's a 0.5%, 0.005 in the right tail, as in the left tail. What I want to look up is the t-score. That puts 99.5% of the distribution to the left. 99% in the middle, plus the 0.5% here on the left tail. We have two tails combining to make 1%. or one tail having only 0.5%. Share my screen and we'll go back to our T-chart. Right. So 2 tails combining to make 1%, or each tail individually having 0.5%. Looks like we're going to use this right-handed column. You could also find the same thing with this 99% confidence level here in the bottom row. Each of the 2 tails combine to make 1%, or one tail individually has 0.5% error. We had 18 degrees of freedom, so I'm going to go down to a t-score of 2.878. These t-scores work pretty much like z-scores. By adding on 2.878 standard errors, by adding on 2.878 standard deviations or standard errors for the margin of error, I've captured 99% of the distribution. All right, I think we'll start getting into creating our own confidence intervals to estimate population means again next time. Thank you guys. Have a good one.